Hello, welcome to the stream. Hope you're having a lovely Sunday. I'm pretty excited about today's stream. We're going to start a new chapter in Essentials of Compilation, excuse me. And we've done a lot so far on this project. I started over a year ago doing these streams, and we've learned a lot. But this one is gonna take it again to another level, and that's kind of crazy. There's going to be some challenges in this, and hopefully you know uh, we've done a lot so far, right? I'm hoping that we made good choices in the last year in certain areas, because they're going to pretty strongly affect how well we do in Chapter 7. Um, Chapter 7, like I mentioned, introduces functions. So these are not lambda expressions. So we're not talking about functions, function values, although they are kind of used like that semantically. These are top level functions. So top level definitions, we let you define as many functions as you want, and then the rest of the body of the program is your main, so to speak. So let's get into it. I think there's no real reason to delay because we've got a lot to do. All right. So this is Chapter 7. And as in previous Essentials of Compilation stream, where we were, referring to the book, I'll have it up here. Early on in the stream, I used the physical text, but that's not really that helpful for showing on stream because you can't read what it says. So here, hopefully you all can see that. Obviously some of the stuff at the bottom is going to be clipped by my video, but if it's too troublesome, I'll move it over to the left. Okay, so we're going to be compiling a subset of typed racket, and in which only top-level function definitions are allowed. Okay, so this kind of function appears in the C programming language, right? You may be familiar with that if you've done any C. It serves an important stepping stone to implementing lexically scoped functions in the form of lambda abstractions. So that's Chapter 8. We're not going to do that for a while because we've got to tackle top-level definitions first. And the things that apply to this will help us implement lexically scoped functions. Okay, so we're going to start. We're going to define the L-fun language, and it's going to be very fun. So the concrete and abstract syntax for function definitions. So they're doing this table thing where they take an existing language, and we can see it down here, and extend it with some new things. So when you see it below a bar, like this is the very first language that we implemented, and then we added let expressions, and then we added conditionals, right? And then we added loops, and then we added vectors, which was the last chapter that we did, last significant chapter that we did. And now we're going to add functions, and this is the concrete syntax, which we're going to have to implement as well. One of the interesting things, and they don't necessarily call this out in the text, but we had a representation. You can see over here on the left. We had a representation of types in our intermediate, one of our intermediate languages, and that was not represented at the lexical or syntactic level. It was only a semantic thing. So after we had parsed the program and created the data structures that we need to represent that program, we would go back and annotate with types. Oops. So you can see that here. Well, now they're actually exposing types at the lexical and syntactic level. And the reason why is we're not going to do full type inference over functions. So it's going to be you explicitly say the type. We'll surface any type errors in your program, but we're going to require you to define what your types are. So this syntax, and let me zoom in a little bit so you can see that better. This syntax here, define, right? So type, this says concrete syntax, but we're not actually, this doesn't actually show up in the the actual printing of the language, right? This only shows up as a concept of what a type can be. So here you can see this is, no, I take that back. Let me rephrase that. We'll see an example down below, but these are actual things that exist in the language. We just never had to parse them before. Now that we have a case where this type non-terminal exists in the lexical language, then you have the possibility of these type terminals showing up in the language, right? Okay. So they're saying the language is, L1 is definition, so a sequence of defs, bunch of non-terminals, and then an expression, and that expression is your main function, right? Adding to the expressions are application, so that's what this is. So you take an expression and you have any number of expressions after it, and you're basically applying that function. And then these definitions, which are top level, they're not expressions. They're a different kind of syntactic construct. You're saying define, var here is the name of the function, and then you have its arguments. And you have a colon, and you have the type, and then you have any expression, which is the implementation, the body of that function, right? Okay, so that's what we're going to do at the concrete level. So the interesting thing about this, and I started to say it and then I took them back. This is actually a type that you can type in your program. So if your function takes a function as an argument, which is valid, it just has to say that this is the type of that function, right? So this is best illustrated by an example. If we scroll down, and I'm going to hide the sidebar so we can fully see this. So here's a function map, which you may be familiar with, but this one is a little bit more focused. It's not generic. So here, the map takes a function from an integer to an integer. And so this function's, this argument's name is f, and its type is a function from an integer to an integer. That's how we represent that type. It takes v, which is a vector of two integers, and it returns a vector of an integer and integer. So, as you might expect, this is creative. The way that this operates is you create a vector where you call f reading the first element of the input vector and call f on the second element of the input vector, and you return that result. Okay, so here's a really simple function you could throw at that. This function increment. So x in this function is an integer, and this function returns an integer, and what it does is adds 1 to it. Hello, welcome to the stream, Akshay. And Kaithera, I hope you're still here. Okay, so then the body of the program here comes after all the definitions, and the body of that program is extract an element from this vector. What is that vector? It's call map with increment over the vector 0, 41, and then take element 1. Okay, so you're going to get 42 because all the programs return 42. Right? All right. So I think let's go back up to the prose here. So we've looked at the constraint. Let's look at the abstract syntax really briefly. the things that are added here, of course, we have types. So the function type is a type that we'll um, need to implement. Your expression, so this new expression here is turned into the apply AST type. And then the def is a def, and you have var and pairs of types, right? And a return type, some annotations which are left empty. It's a racket thing. We may or may not have them. And then the expression that is the body of the function. And then the top level of the lfun language is this program defs expression. So it's like, here's all my definitions, and then here's the expression where they might be used. Okay, that's the abstract syntax. And we've already seen, an example here. What we should do is try to get to the point where we can parse and build abstract syntax tree from this. So let's go back up to the pros, and we're going to have a look there. Okay, so again, we talked about this. lfun, they begin with 0 or more function definitions. The function names for these are in scope for the entire program, including all the functional definitions. So you could think of it like this is going to be multipass. Obviously, it's multipass. That's what we do in this project. But you're not going to have all the definitions and then the implementations like you would in C. You can freely refer to any of the other functions from within functions you define. Okay? So they're in scope for the entire program. That includes the body of the program. Okay, so ordering of them doesn't matter. That's really key here. Concrete syntax for application, we talked about that. Abstract syntax is apply, and this is required in any number of expressions after that. Functions are first class in the sense that function pointer is data and can be stored in memory, passes a parameter to another function. So there is a function type, and we talked about that. Main limitation of these is that they are not lexically scoped. So you can use a reference to that function anywhere. It doesn't have to be in scope because they are globally scoped. Okay? So the only external entities that can be referenced from inside a function body are other globally defined functions, right? So they're saying there's no global variables, right? This is not in a particular scope. You can't put a closure around this function, right? You can't apply an environment to it that is anything but the global environment. And the only thing at the global scope are their functions. Okay. So the syntax of lfun prevents function definitions from being nested inside each other, right? So you can see here that what they're saying is def is a top level thing, and the only thing that it contains, other than the name and the types of the function, is expressions. Expressions don't include define, right? Define is a top level thing. So you can't have functions that define functions inside of them. Okay. Okay, and then they gave the example that we looked at already. So they're doing this racket thing with like extending existing interpreters for lfun. We're going to have to implement or add to our interpreter for lfun. Where do they say it's based on ltup? It's in here somewhere. So the language that we made for tuples, obviously we need, given their example. Okay. Yeah, so they're saying extending ltup. So what we're going to do, I want to get the abstract, what am I trying to say? I want to get the abstract syntax tree built, and then we will go back and try to parse. And I think that that's a pretty good goal for today. We might get further into like maybe doing a pass on that new new stuff, but there's going to be plenty for us to fix. So we're going to duplicate ltoop, and we're going to call it lfun. Okay, so this is our new language. It's basically the same as ltoop, but we get to add stuff to it. Okay, so we're going to start from, let's look at the abstract syntax, because I think that that's probably the best place to start. And I'm going to, for now, hide the project explorer and the shell, and we're going to get this side by side. Okay, so we need a type for function. So I'm going to call it fun. And this is going to take, I want to name these. Would you say arguments or parameters? I don't know. This is going to be a list of type, and return is going to be a type. Okay, so that's essentially gives you this arrow, right? We have, let's say arguments. I'm going to be a little bit verbose. And then return type. Okay. So we might need another type error, but let's come back to that. This is not a primitive operation. This is an expression. So we're going to say the expression is apply, and then the function is going to be, that's going to be a string identifying the function name. And then the arguments are going to be a list of expressions, right? The thing is, actually, this is an expression. I got that wrong. So this is an expression, not a name. It's interesting, you know, we have all these primitive operations. You could express a lot of them in terms of apply and do a different, like do a level of lowering where you identify the built-in operations and lower them into a primitive form. But we're not doing that in this example. Okay, so our program has a bunch of definitions. And this is going to be a list of definition. And we need to define that type. Okay. So a definition, we'll just call it def to follow what they have. So this is going to be the function name is going to be a string. And then we're going to have the arguments, which is going to be a list, and I'm just going to say it tuples, and this is string because it's a variable name, and type. Okay. Return is going to be a type, and then body is going to be expression. Okay, so we've got def. And now our program has, you know, I don't know why they name it differently. Maybe it's so there's no collision or something. Yeah. Okay. So we could look at, let's look briefly at 7.4. They're doing, there's a fun, we need to go back and look at some of the, okay, look at the text. So the definitional interpreter for lfun is shown in 7.4, which we just jumped to, but then that lost context, and that was not great. The case for program defs xast is responsible for setting up the mutual recursion between the top level function definitions. So this is like, how can they call each other, right? We use the classic backpatching approach that uses immutable variables and makes two passes over the function definitions. Okay. There's a reference here. You jump to, right, so this is a scheme thing. Can we go back, please? Go back. Okay. In the first pass, we set up the top level environment using a mutable con cell for each function. So basically, you're saying what they want to do is make a dictionary for the environment, and the environment contains functions. Note that the lambda value for each function is incomplete. It does not yet include the environment. What are they saying there? Okay. Let's look at their interpreter real quick and see if we can learn something. Okay, so they're inheriting from the interpreter for the previous language version, which is what they do a lot. Okay, so then it's, recur is just call the parent version. And then if you have apply, then you call interpret on the function argument, right? So this is treated as an expression. And then you call interpret on each of the arguments. And then if the function value is a function, blah, 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 and this is some macro magic and racket that we don't have, but this is basically, you could think of it like decomposing this value where you have xs as the arguments, and you have body and fun in v here. Okay, so then it's across all of these arguments, we're taking, right, so we're taking one formal argument and one real argument, and we are putting them together. So we're stuffing them into pairs. Okay. And is that what that does? Cons x to box arg. That's interesting. For list. Okay. So it's turning them into pairs. Like here's your value, and x is the name of the the argument, right? Okay, and then it defines a new environment by taking the global environment wrapped around this function and adding these. So it's basically saying, how do we interpret this expression in this function? We have to take any global environment that it has reference to, basically all the other functions. And then the way that its arguments work is you basically pretend that they're in the scope around this expression. It's like you can pretend that this is let A equals this and B equals this and C and so forth with all the arguments, and then evaluate this expression. So that's what this is doing. Okay, and then it's recursively calling the interpreter with that appended environment over the body of the function. Okay, and then for anything else, it's like, hey, we just use the stuff that was there before. Okay, interpreting def is a new thing, it looks like. Yeah. So this says, if this is the syntactic form, then what you want to return is a pair where f is the name, right? And then it quotes a function. So that's what gets decomposed up here, and it starts with an empty environment, so empty dictionary on that function. And this is just for the interpreter, right? This is not for the language itself. This is just interpreting the language. And then for interpreting the program, so you've got, so they're destructuring this, the top level program, and then it says, so you interpret the definition of all of the function definitions, and then for all of the things in the top level, so it's unboxing that, I'm guessing, yeah. So it's basically saying this is building up a dictionary of what is the definition of each of these functions, and put them in the global scope. Well, that global scope gets to be injected into all of the functions for their local scope. Okay, and then you take this this environment that you've built at the top level, containing all of the functions, and all the functions with all the potential references appended on into their environment, and then you interpret the body of the program using that top level environment. Okay, so the set box is a mutable thing, right? Okay, crazy. And that box is just to make a mutable cell. You know, you could do it with functional transformations. They just do it differently in Racket than we do in Gleam. All right, so that's the interpreter. I think that like that's pretty good. And if we go down here, like for our I value, we would need a function value, right? So, and the function value does not contain the name, interestingly. So we say fun value, because it's very fun. So arguments is going to be, again, a list of string to type. And then, and maybe won't get to this, but I think I need to go ahead and fill this out while we're thinking about it. The body is going to be an expression, and the environment is going to be an environment, right? Oh, okay. Well, we can say, the thing is, the environment doesn't need the heap for this. So we could just say it's a dictionary of string to I value, right? Because that lets us, you know, recursively put the the thing is, I feel like though yeah, this is not going to work because you can't have circular references in Gleam types. So I think that what we'll do is, instead of this, we'll just have to do something different with interpreting, right? We might need to have when we go to evaluate a function, we might need to take that global, like keep a global version of this. That's interesting. Okay. Let's see if we can figure that out. I think that's probably a worthwhile thing to do today. All right, so our big problem here is we need to handle apply. Okay. So function is an expression, arguments is a list of expressions. So we can go back up here and see what happens. Okay, so we need to call fun val is interpret expression function env. Okay, so we've evaluated that. Let argvals, and we'll just do list map. Right, list map over arguments, interpret expression env. Okay. All right, so we need to look at this is where we get into what is this, right? Oh, this fun val is, we need to, actually we don't care about, those don't escape that expression, so they don't create a new environment. And the same for the arguments. Okay. Okay, so that gives us a list of values, and that's an I value. Okay. I just lost my spot. Here we go. Okay, so we need to make sure that this is a function. So we need to, they're doing match fun val. We have just been doing panicking in here, right? So we should say that this needs a let assert on it. And we could probably do the let assert here and just decompose it. Fun value. Arguments. And body. Come on, work with me here. Body, okay. Okay, so the problem here is, we'll call it formal args. So now what we want to do is we want to create a new environment. So the environment type is the variables, the local variables, and the heap. So I think that what we'll do is the interesting thing here is we could combine these. The other thing that we could check here, and I don't think that's important for the interpreter necessarily, because we do have a type check phase as well. But we could check that the number of arguments are equal. So we could say assert length of arguments, a little sanity check here, length of formal arguments, because we don't let me put a to do here at the end. We don't support like unused arguments. We don't support or like empty arguments or optional arguments. Okay, so let me rethink this, because what I want to do is we're basically going to construct the new environment, or let me say new vars, right? And that's going to be, we're going to list fold, and we're going to figure out what our first argument is there, what list we're folding over. But we're going to start with env.vars, right, which is okay, so our accumulator, and then what we want is a pair of here's the argument and its value, right? And ultimately we want to say dictionary insert into accumulator, and let's go ahead and make this. This is going to be list zip. We've already checked that they have the same length, so it's not going to be a problem. We're going to zip the formal args with the arguments. So the first item in this pair that's going to be the variable name, and then the value is going to be pair.1. All right, so oh no, what we need to do is go let value is interpret expression pair.1. Sorry, I forgot we have to interpret it env, right? And then we go value. Okay, so we built up the new variables, and then what we do is we go interpret expression over the body, right? With extending the env with the variables is new vars. Okay, I hope that was, let's convert that to a pipeline. And convert that to a pipeline. Okay. We could do that with use or something, but it's fine. So what we're doing is we are evaluating each of the given arguments. So we're interpreting that expression, and then we're taking the resulting I value and adding it to the environment, just as they do here. So I don't remember why they need a box. Ours is a non-mutable language, so we don't need to bother with worrying about whether something is modifiable or not. Okay, so we have interpreted function application. Pretty sweet. I think what's neat about this for me is seeing that when the body is just an expression, then function application is fill the environment for that expression with all of the arguments, and then evaluate that expression. That's, I don't know that that's a huge revelation, but it's sort of like, oh, that is actually simpler than I thought it was going to be. When you're talking about interpreting, obviously when we're talking about compiling, it's something else entirely, and we need to deal with that. Let's see what other problems are in here. Okay, so type checking. Let's look at their, oh, and we need to deal with the, we need to deal with I think we need to type check definitions. So we'll need to build some stuff for that. We'll make a type check defs, and it's probably going to be, and this is going to be a result.map, right? So that if any of the definitions don't make sense, then that will be returned early. And then here we're going to say, we'll just call this body, and this is defs body. Okay. This is actually going to be result try, not map, because this is, and so of course it's like, we haven't defined that. Type check defs. And this is going to be a result list of definition or type error. And we'll put to do on it. Okay. Let's look at expression. We're going to have to make another clause for apply. Right? And we'll just leave that to do. Are there any other places? Let's see down here. All right, so we have to, why is that not formatting? It's something that's messing up above. Oh, it just like had a glitch. Okay, let's go up here. So format expression, this should be straightforward to do. So we're going to add apply. And want to do... Ultimately, this is going to have parentheses around it, so we'll make parenthesize. Remember, this is just for pretty printing, right? Ultimately, that's going to be there. Right, okay, so that's fine. So let's do format expression of function. Right, so we're basically going to append or prepend the function expression to the list of arguments. And then we will, this is pretty straightforward, thankfully, concat join with doc.space. Okay. I mean, not much to say there. We didn't really add anything new. It's very similar to like set bang or let, with the exception of let has, you know, a bunch of keywords and things in it. So that was straightforward. Okay, so format type, add missing patterns. All right, this one is going to be trickier. So the function type has a list of arguments, and ultimately we're going to do concat join again with doc. What is flux space? Yeah, let's just use space. Okay. Okay, so we are going to do... oh, right, and then this needs to be parenthesized at the end. Similar to what we did in apply. But here we're going to say let's do it like map over arguments with format type. Is this really the best way to do this? Yeah, I guess so. Okay, so then we're going to append two things. We're going to say doc from string, and it's going to be the arrow. And then format type of return. Okay, so we format all the arguments, we put an arrow after that, and then we put the return type, the argument types, and the return type, and then we join those with spaces, and then we parenthesize, and that's what we're showing up here. If I can go back fast enough, like this is what that looks like, right? Any number of types, arrow, and then the return type. Okay, we're going to need a format def, but let's go back up and here we go. So we have it to do here. This is the type check. We have it to do here in type check defs. I think we should also have right, we need to interpret the environment. I'm sorry, interpret the definitions, right? So we need to say let env is interpret defs of p.defs and a new environment. And then we will pass that here. Okay. So we're going to need a function interpret defs. And let's use the code action to generate that. Cool. All right, and now we can go back and look at what they do again in their interpreter to fill in that information. So we kind of have a chicken and egg problem in that we don't have mutable cells in Gleam, but we want to know we want to keep the top level environment. And I want, it's making me wonder whether we need to change this environment instead of just being there's a bind var function. That's pretty useful. Maybe I should have done that. Instead of being just a flat dictionary, we might want it to be like nested. With a distinct top level, because the functions, when you apply a function body, you have to, like, let's go down where we did apply. Where it is, where did it go? We interpreted apply. Using the current environment, but we don't allow closures. So we need to get the top level environment. Which to me says we need to have a separate thing for definitions here, right? Okay, so we had this idea of, you know, allocating a vec. You would create a heap reference, and that would just refer to someplace in that heap. And it's almost like what we need to do in our interpreter rather than what they did is have function references. Here we've kind of assumed that interpreting Yeah, there's a bit here that is not correct, at least not consistent. And what we're going to do is say this is new E and V. Another way to look at it is we could we want to reuse that function. We could say that there is a top level definition in this environment struct. Sort of like this, you know, fake top level business here. And we could do something where we make a global scope, and this takes an env and returns an env, and basically eliminates all the local scope. So the other thing there is we kind of want a bind top level. And we're going to have top level, which this is going to make discovering or like binding things interesting. String to I value. Okay. Dict.new. So global scope is going to be, we're going to take this, but we're going to say vars are empty, right? So that's saying like you can only treat things that are in the top level, and we're going to have to figure out the places where we're directly pulling things from vars rather than using a function to wrap it, because it should be like try to get it from the local variables, and then if that is not present, look in the top level for something. I think that that's probably the way to go. Okay, so global scope. Okay, bind top level. What we want to do is say keep E, but top level is E dict insert into E dot top level for D value. Okay. So then for apply, what we want to do is rather than fold over E, we want global scope over the env, right? Because the body of this does not exist in the local scope. It's only in the global scope. Okay. So now interpret defs is going to be, we're just going to list fold over defs with env as the input. Okay, and then we will do so the definition, we need to turn it into a fun value. It's very fun. So we're gonna say bind top level env, and we want to use d dot name, and then we're gonna make a fun value d dot arguments, right? And then d dot body. That wasn't hard. Except we need to use the right thing there. Okay, so interpreting the definitions is really just put them in the top level of the environment. Okay. So that way, when we're interpreting a function application, when we get this down to a fun value, that body can refer to anything that was defined at the global scope. And then we zip the arguments together to interpret the body of that function. So we need to find where get var. So get var needs to go here and say we're just going to add another case expression here. And there's a way to do this. There's a way to do this more elegantly, but we're going to extend that to say, you know, you referred to unknown variable or definition. Yeah, we could do this as a like map error or something. Lazy unwrap, maybe. Let's see what the standard lib has for us in result. Okay, so we can do try recover. If you do not need access to the initial error value, use result lazy or. Okay. Returns the first value if it is okay. Otherwise, evaluates the given function as a fallback value. Okay, so that's what we want. So let's rewrite this. So we're going to say use result.lazy or. Okay. Oops, our arrow got chomped. Okay, so if it's in a variable, then we just return it. Lazy or returns a result though, so we're probably going to have to figure out how to unwrap. And honestly, that's probably let's do it without use first, and then we can transform it into use. So lazy or, if we don't get that, then we do dict.get. Okay, so this, I'm sorry, I was looking at lazy unwrap. Lazy or, so this is going to return a result, right? This is actually not bad. Let's convert that to extract this panic, sorry. I think the thing is I want to panic inside. Problem is a panic, we could just try it, I guess. Result.lazy unwrap. Okay, that's not the prettiest. Let's turn that into pipeline. Okay, so basically we're looking in the variables first. If that fails, then we look in the top level. If that fails, we panic. Let's see what we can do here. So both of these take, we can convert this to use. So we're going to say result.lazyOr, and then we'll put that in there. And then we'll use result.lazyUnwrap. Of this. And then we put this here. All right, now what's the problem? Oh, I see. Let's undo that. That was not good. This is fine. I like use a lot, but yeah, it's kind of like the unwrap has to go on the outside, and you know, the problem is there's two functions here. Okay, I think we've done enough with that. Now what will happen is when you get var, which is whenever a variable, you know, it's just a name, that's expected to be in scope when you refer to it inside an expression. So if that refers to a top level function, then that will be bound to that fun value we created here, right? So if you eventually get it down to a fun value, then we can do this apply properly. So that was a missing link. So yeah, we're doing 240. Excellent. Okay. So we need to do type check of definitions. And let's see, what else do we need? Yeah, and we don't have a type check of apply. So there's a we need to go through the definitions as well. So if we decided, assuming that this has already been implemented, we need to make the top level and we're going to say list fold, and let's pass in the top level here, right? List fold over defs with dictionary.new, and we're going to do basically what we did for the values in the interpreter. We need to, right, this needs to be a dictionary of strings to type, the type environment. So let's say insert accumulator, and this is going to be a definition, but we need it to be a function type. So yeah, I think I want to rename this to FunT. Yeah, let's do that. FunT, to distinguish it from function values and function definitions. We'll just say, you know, all of our types end in T. Okay, so so this is a FunT, and we want to, let's look at list real quick, because the definition has the type in the second thing, so we could do unzip. And just ignore the keys. Unzip d dot arguments. That gives us types. So this should be a list of type. Yep. Okay. So arg types, and then d dot return type. And we're going to insert that into d dot name. Okay. So now we have the top level types for those functions, and then when we go to type check application, we can make sure that that those are present in the type environment. Okay. So this gets a little bit tricky with type check defs. I think that this really should be like a result.all, right? That's what our final thing should be. And we're going to take defs, and we're going to map over that. There's an inherent problem here in that we don't necessarily have the types of the definitions. Let's, you know, before I get too far into this, let's look at what they do in the book. Okay. So for type checking, so they had, there was a check type equal thing in previous versions. Wow, that's some bonkers racket. Okay, so what they're doing here, this is what we did a bit ago. This is like definition to function type. This is take all of the parameter types and the return type, and that's what they're returning. We can make a function that does that. It's not a big deal. Okay, what do they do? So, okay, so they just assume that the function, right, so they build this environment before they look at the definition, the type checking the definitions. Okay, so we're going to do that. Let's move this up, and we're going to say p.defs, and then we'll say top level. Okay, so it's going to take a type environment for that stuff already. And let's extract this. And they've got this definition name here, kind of like a function reference, I'm guessing. Okay, so basically it's right. Check that the type of the body is an integer. Check that all of the definitions, type check over that global environment. Okay. So let's see here. Okay, so for each definition, we're going to take each of the parameters. Yeah, since they're using lists of pairs for their dictionaries, like they got it a little bit easier. But we're going to fold over the arguments into env and say pair, and that's going to be insert into env pair dot 0 pair dot 1. Honestly, there's probably a way to do this with just like append with a list. Okay, so that's the environment for for type checking the body. Okay, so then we're going to say type check expression. Yeah. D.body and the new environment. And what we want to return from there is needs to be try check type equal of so this how are we using this elsewhere? Right, we're excited like what the expected is, what the actual is, and then the expression. Okay. So what the expected is d dot return type, and then the body type, and the expression is body. Okay. And then check type equal returns resulted nil or error, type error. Okay. So then finally what we want to do is if that all passes, then we just return D, right? That doesn't seem so bad. So let's compare here. Okay, so we've got a definition. It's got this name. Oh, right. What we want to do is say definition, splat D, and the body. Replace the body, right? Or they called it def. Okay, right, because this type check expression could modify the expression in body. I don't think that we've made use of that yet, but oh no, we have, because for vector types you have to annotate them with has type wrapper. So we need to make sure that that gets propagated if there are any allocations inside a definition. And honestly, I kind of hate that that is a different name. So let's, oops, not here. Okay, definition. Okay. So what else are we missing? All right, so now we need to apply. We need to type check apply. So let's look at what they do for Okay, so this is the type check apply. I don't remember what this values thing is. Or why there's apply and call at this level. I'm a little bit confused. Do we have a call at a top level expression? I didn't think so. No, we just have primitive operations. I don't know what this business is. That doesn't make sense. Or what funref is. So let's see if we can find out what funref is. And they start talking about functions in x86, which we're not going to get to today. But we will probably next time. Because we need to think about, you know, all of the calling conventions and so forth. As well as how do you refer to functions at the assembly level. Yeah, I don't see a funref thing. Okay, let's go down. And maybe if we get far enough into this to where it will fully compile, what I mean is our function or our language definition, then we can go and update the parser, and hopefully that won't take too long. It might. We'll see. Yeah, I don't see where they're talking about funref. That's got to be something else. Maybe that will come up later. Okay, so if we have an apply, so we're looking at type check. Okay. If we have an apply, we need to get what is the right. So what is the type of the function, right? Okay, so we're going to say f type. Function env. Okay, so that's like, can we evaluate to a function? And here, yeah. So this is just, you know, this should be, and we can't really do check type equal here, but we should be able to do something like check that it is a function, right? We'll just say check type is function. And then we'll say f type, and then the expression is f. That's sort of the convention we were doing. Let's define that function here. We'll just say to do for now. Generate function. Okay. So here, let's just say result nil. Okay. Here we want to say case f type, and then if we say we just ignore that, and we'll say okay nil. Otherwise, we need to say type error. And here's where we're going to get to add a new type error. Okay, so this is an expected actual expression. Here we're saying the type error is a application to let's say function application. Let's just call it that. And the actual is a type, and the expression is an expr. Okay. So check type is function. here we're going to say not type error, but error function application, and the type is f type, and yeah, let's just not make typos. Okay, so so that's just making sure that we get it is a function. Okay, so now we need to check that on the function type that all the arguments that are being passed, right? So okay. So now we'll go list map okay. So we'll do list. We need a zip, right? Zip these two lists together. So we're going to say f type dot, let's see, they're doing the argument type and the parameter type. I always get confused about which one is. Okay, so the argument type comes from the definition, and the parameter type, I should rename this. Yeah, we'll go and fix that later. Okay, so we need to take there's a problem here in that this check type is function is not real great. Yes, hello Bianca. My cat's talking to me. It's not great in that we're not getting any of this out of it. So maybe let's not do this. The other option is that we can have it return arguments and return type, or RT and return type. And then this is going to be list of type, and then we have it, you know, extracted, and we've already checked that it's correct, and here we just go, rather than not binding these, we've got them, we see arguments and return. Okay, so so now we can make use of these rather than having to go back and match on this after we've already matched on it once. Okay, so we're going to take RT and we're going to zip it with arguments. And then we will map over those. And finally, we're going to say result.all. So mapping over those two things, what we want is check type equal, And this is going to be, so we're expecting this, and we got this, and the expression that we want is apply function arguments. It's actually just E is the expression. Okay, so this just returns us so check type equal we'll do this business. Oops. Except we need to do right. So what we didn't do was map over the arguments. We need to do, rather than this, because that's not a type. So we need to do let P and P type result map result try. Sorry, getting a little bit dizzy here. So we need to type check the expression that is pair.1 in the environment, and then we need to check that the argument has that type, and then finally we are going to so there's a question in my mind here about, like, this needs to return and apply at the end. So really we just need P. Okay, and that's going to return okay, so let's have this we'll call it checked args is this. And what's the type of this? Result of list of nil. So this is result.map here. Okay, now it's a list of expressions. Okay. So if we've got that, we've essentially done what we expected here. Let's look at what they do. Type. Okay, so the expression of the function and the expressions that are their arguments. Okay, so what they're doing it in a bit slightly different order here. We have this check type as function. this e hat with its type. Okay. And then I don't know what this for lists is. It looks like they're doing. Let's see if there's another example. There's for list, not for lists. Yikes. Okay. Okay. I think what's going on here is this is going to return a pair of the modified expression and its type. This in list gives a binding from an element of this ES list to E, and then you type check it. So this is a really weird expression, and I don't fully understand it, but I think that we have an idea of what we want in scope here is E star and tie star come from doing type checking of all the arguments. Right, so we're kind of doing that here, but we're doing it as like in line with looking at the types of the function definition. Okay, so then they're going for all the arg types from ty star and all the parameter types from here. So ty hat star is all the types in the function type structure. Okay, and then they're just saying check if they're equal, and we're doing it reversed. I think it's better to say the this is supposed to return expression type. Okay, so okay, sorry, had to do that without talking. Okay, let's walk through this again because I think I've got it, and it had to do with looking here. So we're type checking the expression of the function. So we want to make sure that we get what is being applied to those arguments. And then we check that the type is a function. And if we've got a function, we get its argument types and its return type out. Okay. Although they say parameter type, and it's fine. Okay, so then we're checking the arguments that are being passed. So we zip the types that we determined for the function together with the arguments that were given, the argument expressions that were given, right? And then for each of those, we type check the argument expression. and we get its type out as well as any transformations that happened on it. And then we're going to check, is the formal argument type equal to the inferred type of that expression that's being applied in that argument position, right? And if it is, then we return it. If not, we return the type error. And then we call result all because, you know, there's multiple expressions for arguments here. And then we're just saying if all the arguments check, and you know, the function is the thing being applied is a function, all the argument types match, then we can say this is a, you know, checked args is a result of a list of expression or type error, and then so we map over that and return you know, our transformed application. And actually we probably need to use f here, not function, because we need to take that expression, right, and put it back in there. So that's what they do here, right? So they're saying run this expression and bind the result to E, ES, and return type, which is what's returned here. So the transformed function value, function expression, the transformed arguments expressions, and the return type. I think I'm getting this define values and values. Values is like, how do you have multiple return values? Here we just use tuples or structures. In Racket, they're doing something else. Okay. So I don't know what we do about funref or call. Those are things that I think will come later. But I think we've kind of handled type checking. And we have no more warnings in here. So let's do a Gleam build real quick. Yeah, clean. Okay. Now we get to break shit. Excuse my language. Let's take a quick look at our type check program. Make sure that that's okay. Right, so we did, yep, give me all those. Turned into function types. Type check the definitions. Yep. And then all right. So, and we have our formatting. So I think that what we can do is, to wrap up the stream today, is let's look at parse, because we need to look at this concrete syntax. And let's see, are there new tokens? Yes, there are. So we need a new token type. Let's look at, what are the tokens? So our punctuation is here. Token, we're going to use colon. And I think that everything else is handled, with the exception of we need to deal with what is this set that's being passed? Let's look at that on hex docs. Okay, identifier is a start, inner, reserved. Okay, and to value. Yeah. So we need to handle types. And I think we're just going to brute force it for now. We'll say type name string, not string. Yeah, we're gonna have to do, let's do lfun here. And that's gonna be lfun.type. Let's just do string for now. And here, let's do integer or Boolean or void, and that's going to be type name text. The other thing is going to be a vector, right? Because that's a type name. We're not going to use, like, we'll turn that into the proper thing when we get there. So okay, so let's look at, so parse is body. I might have to refer back here. There was sort of a thing for sequences. All right, so these are taking little bits. Yeah, one of, where's the begin thing for, like, because while, okay, so expression, so nested, that says paren one of these things, and then a close paren. While expression says keyword while, condition is an expression, body is an expression. Yeah. Okay. Interestingly, I think none of the things that we have, well, let's look at vector op. Vector op's the interesting one. Okay, so it's just many, right? So looking at many, so many or many one, right? Okay, so we're gonna say, let's look at the program, and then we'll kind of do it top down. So we'll say use defs is do nibble.many definition, and this will be a list of something, right? So let's look at our program type. Program. So it is called defs. That's easy enough. I'm glad I named it that. Okay, so we need to make a parser for a function definition. So let's generate that function. Okay. So this is going to be, it needs to consume an lparen, right? And at the end, it needs to consume an rparen, and then we'll return def, right? Okay, so let's look at some of these examples. The other thing that we need to do up here is there's a keyword that we need to create, which is define. And we need to handle that. So here we're going to say define is a keyword. Define. Okay. So let's look at the syntax of that and the concrete syntax and so forth. Okay, so we have define. Keyword define. Okay. And then we need a name for the function. And we'll do lang.definition here. And let's name arguments return body. So let's just pretend that arguments return body. That we will, let's pretend that we will have bound these, right? Okay, so we're gonna do a how are we parsing this elsewhere? Expression, so we need identifier, right? So this is going to return a string. Okay, so let's say there's an identifier. Okay, so that gives us a name, right? Now we need to do, I'm sorry, so there is define, and then there's another open paren. And then there's identifier. Let's look at the example as well. Okay, and then there's going to be an argument. So let's just pretend that this exists. Nibble.many argument definition. Okay, so we're just going to pretend that that exists. And then there's a close paren. And then we'll say and then there's going to be a colon. And we're going to say type is a thing, because we're going to have to do that inside here as well. So type needs to have a parser. And then we're going to say, and this is actually return type. We'll call it return T. This is return T. Okay, and then we have an expression for the body. And then we have the close paren, and there you go. Okay, so we're going to have to do We're going to have to make an apply expression in nested here as well. We're going to do that, right? That's undefined. And we need a type parser. Do I already have that defined in here? Nope. I think the problem is I need to do this because that's a reserved word. Okay, now we've got something. Okay, and we need argument definition. Here, let's generate that function. Thank you. Okay, so so here we're going to say we want a bracket, L bracket. Yep. So we have an L bracket. We have var is a identifier. We have a colon. And then we have ty is a type. And then we have our bracket. And then we return var and ty. Okay, so our argument definition wasn't that hard. The main thing here is that each one has a bracket around it. There's no like commas or anything. Okay, so we need to look at how to do the type parsing because it's going to be a little bit tricky. I think that it's either going to be it has to be a scalar type or it's a vector type. So I want to look at how we've been doing that before. All right, what does take map do? Takes the next token and attempts to transform it with a given function. Okay. We might need to use that. Okay, so let's maybe build this one up a little bit from the bottom. Let's see, we're at 336. So let's do a scalar type. This is going to return a lang.type or antics token. No. Because what I want to do is have basically a one of. And this is going to be scalar type or vector type, right? There's also function type. But I think that we need to do vector type first because that's going to be more specific. Okay. And let's do generate that function and generate that function. Okay. So a scalar type serves the take map. Take the next token and attempt to transform it with the given function. This is useful when, okay. So if your function looks at the token and returns option of the thing, then you've got it. So scalar type, I think what we can do is we can model after that comp op or comp inner. Right, so it's take the token and produce an error. So we can say token, and this is nibble.take map. And we say expected type name. And then we say case token of, and we'll make the fall through case first. Let's say if it's a type name of integer, then we're going to say some integer t. Lang dot, right? And then we'll do for Boolean, we'll do Boolean t. And I don't think that we really will support void, but it's there. And if you look at the, the types listed here, it's there. Okay. So that handles the scalar types. Now we need to do the vector type. And we're going to say we want token. Come on, Sean. So we say token of lparen. And then we want to make sure that it's a vector. So we'll say nibble.token type name vector. And then we'll do, we'll call it field types. And actually, let's look at the vector t. It's just, yeah, just that. Okay. Then we're going to do nibble.many. Of type underscore, right? And then we will do nibble.token rparen. And finally, we will return a lang.vector_t of field types. Okay, that wasn't so bad. Now the function type is going to be fun. So we need to make sure that we have arrow as a token, right? I'm going to move this up. Arrow. Except, no, I think this is fine. I'm wondering, yeah, I think we need to put this in here rather than because we need to handle disambiguating. And I'm just gonna do like so. I don't know that this is the right way, but if you look at this, the start has to be anything that's not 0 through 9 or open or close parens or open or close brackets or curly braces or quotes, commas. Right, so that would include this. So I think we need to handle this here. Otherwise, what we get into is what we had before. Like, these all have to be unique, right? Otherwise, you can get a situation where one of these earlier tokens matches, and it could have fallen into here, and you have a valid identifier name. So honestly, I think that we need to do this as well. Because that's covered by this regular expression. And it's basically, these are excluding spaces, right? Yeah. Okay, so now we can handle function type, I believe. Okay, so we're going to have an open paren, and we need to make sure I have a closed paren on it. And then we're going to have, we're going to say argtypes is going to be many of type. And then we're going to have a single token, which is going to be an arrow. And then we'll have one type. And then finally, we're going to return fun_t, right? Let's rename this to arguments. And underscore there. Okay, so now we have a parser for all of our new constructs, I believe. Let us see where there are bugs. Okay, so we need to apply expression. So apply expr. Here, let's just generate that function. Okay, so this needs to return an expression. So what we need is so nested handles the parens. What we need is the function. We need one expression there, and the arguments. And then we return apply f-args, right? This really needs to be very carefully put in here, because if you don't, then like special forms will get usurped. I believe that one of, tries it in order. That's really important, because all of these things need to be handled before you apply generic expressions. And the fact that the function that's being applied is an expression, not just an identifier. I mean, maybe we could limit it, but if you look at this, they're saying, well, it can be any expression in function position, and then you apply these arguments to it. That's really powerful overall, but we need to handle that. So we need to make sure that all of these things are checked before you just assume it's apply. The converse of that is if you treat built-ins as function application, you get more flexibility at the syntactic and semantic level, but you also get the possibility that someone can rewrite, they can redefine a primitive, and that's not what you want. Now we should probably put in some checks that they didn't redefine like plus. That's kind of important. That said, what would happen is that would show a keyword in identifier position on the define, and so that would bail. Like it needs to be an identifier in definition, so like it wouldn't parse correctly. So I think that we're okay there, right? Because I called identifier here, right? And identifier is way down here. It's saying if it's an identifier, take it. Otherwise, you expected an identifier, not keyword plus. So you can't override existing interesting. We don't have times and divide, but okay. Anyway, do we have that in a prim up? No. We have plus and minus. We don't have multiply and divide in this language. That's really interesting. Okay. So I think that the last step for today, and we're going to hide the book for a minute, is to go and look at our tests and see what we can do for the parse test. If we have one. Yep, we've got the parse test. Okay, so we need to rename this as L fun. And there's going to be a lot of tests that break. So, right, so defs is, so it's just going to be empty list. And here again, no definitions. Let's do some token tests. We need to put something in here that has a definition. So we'll just say define ink. And this, remember, needs parens, ink, x, integer, and we'll say that returns integer, and it's going to do plus x1, and we need to handle that. So let's just fill it out here. We're going to have lparen, keyword define, let's go ahead and put that in there. Define, we need colon, and we need arrow. Those are the new tokens. We also have type name. Yeah. Okay, so define, and then we're gonna have, okay, so then we're gonna have lparen identifier ink, and then we'll have bracket identifier x colon type name integer, r bracket r paren colon type name integer, and then the whole expression there, lparen plus keyword plus identifier x integer 1 r paren r paren. Okay. So that includes all of our new keywords, the type definitions, and so forth. I want to do one with arrows in it. Let's put colon in there and arrow just to make sure that they will tokenize out. So colon arrow. Those are punctuation. I need to get away from using should.equal, but not today. We're going to do parse defs test, and we're going to make that our last thing that we do today. So ultimately we want to parse this, right? And that's a complicated syntax tree, but we're going to do it. Okay, so we're going to say, similar to this above, tokens should be okay. Parse should be okay. And then let's just start with that. We're gonna break a bunch of stuff. Yeah, the problem is the whole thing doesn't compile. So we're gonna have to go through and deal with that later. Yeah, all of these subsequent phases rely on the fact that parse doesn't use a different language, output language. So yeah, that's a bit of a problem. Interestingly, like it's just the tests that are failing to compile. So I think the answer is, let's comment that out. We're gonna have to make some tests for interpreting lfun, but we can do that next time. So this is a big problem. I think we just go up here and we say lfun as L. And then we'll just say that for now. What else is broken down here? Yeah, this is starting to get into we should probably not expose some of this stuff yet. Because the types don't match up on those phases and so forth. So yeah, that's a bit of a problem. All right, I need to call it. We're half an hour over my usual length, but we will continue with this next time. And there's always a challenge of doing this from the front end toward the back rather than the other direction, in that you're going to run into these things where your existing code breaks. And I'm grateful for Gleam being so persnickety with me, but it does induce a burden where I need to make sure that I've got all my ducks in line before we move forward. So next time we'll start looking at fixing some of these bits that are not compiling, and then we'll start implementing phases, and that'll be a much better spot to be in. So thank you for hanging out, and hope to see you next time.